anyway. And that's the theory of stochastic process. So an example of it, the simplest example, is the theory of the random walk. And so in this opposition, I would say that the histories-based approaches make quantum mechanics look much more like a generalization of the classical stochastic kind of physics than they do like generalizations of the deterministic Hamiltonian evolution. And then a final thing is, this is related, what is most characteristic of quantum mechanics? And my list, I had the superposition principle. Many people would say that. I also had the non-commutativity. This is my shorthand. The natural symbol is my shorthand for commuting. So non-commutativity, and then finally, I think the answer that I would give is that it's interference. If you want to see that it's interference between different processes or different alternative ways that a process can happen, space-time alternatives. And that one, just as Ball claimed that everything followed from this, I would claim that everything follows from this interference among different, like a diffraction, different interference among different paths that the diffracting object can take. So in fact, if you want to read, I mean, as some of you might, so as I said before, when I talk about history's interpretation, it's at a technical level, it means the kind of interpretation that belongs with a path integral formulation. Indeed, it's an attempt to make this path integral formulation a freestanding foundation for quantum mechanics, including at the interpretive level, ultimately. Some of you might know that I think the path integral was first introduced by Paul Dirac in an attempt to explain how the classical limit came about. And then, of course, it was very much more developed by Feynman. And so, if you read, some of you probably have seen that little 3-volume. I think they used to have a red cover. I don't know if they still do. Then there's lectures on physics, and the 3rd volume is an introduction to quantum mechanics. It's the course that he gave at Caltech to the undergraduates, and that very much. Although he didn't always talk about it in the more graduate, like I took a graduate course that he taught, he didn't hardly talk about path integrals in that. But in that undergraduate book, he's really presenting the first half of it, if I remember it right. It's very much a histories-based way of thinking about quantum mechanics. So if you read that or have read it, that maybe can put you in the right frame of mind for what we're doing now. So these are the ones that it's this mode of thinking about the quantum world that corresponds to what I'm calling the histories approach.
You're still going to use complex numbers?
Yes, I'll use complex numbers, and in fact, it's either a shortcoming or of the histories-based approach, or it's something that points beyond it. That it doesn't have a clear answer to why we need complex numbers. So as far as I'm concerned, it's still a little bit mysterious why nature doesn't just get by with real numbers. It has something to do with what you might call, I think it has something to do with the mark. Well, it shows why we have complex numbers, I don't know, but the difference between having complex and having only real numbers shows up, as far as I know, in 2 different settings. In composition of subsystems, they would compose very differently if you have real numbers than complex numbers. And in evolution, the fact that the Schrödinger equation has complex numbers is what apparently allows, this won't be clear at the moment, but it seems to be what allows the evolution to be Markovian in a certain sense, whatever that means. But anyway, so it's clear that complex numbers are crucial somehow in nature, but exactly why they have to be there is not something that I have a good answer, that this kind of approach so far offers a good answer to.
People says that, People says that instead of complex numbers, we go to R2 and define some appropriate algebra. Does that help in any way?
If you go to R2,
Means we introduce two real numbers to describe.
Well, you could certainly always regard, I mean, of course, you can always just say that
So
a complex
that
number is
helps
just a
us
pair
if
of
we,
real numbers. But that's not what you mean, is it? You mean some other algebra than the complex?
No, not just multiplication of real numbers, multiplication which comes in the form as multiplying two complex numbers.
Yes, it could come about that way. It could be that the complex numbers are sort of accidental. The essence of it is just two real numbers. But yeah, I don't have anything, I think, useful to say. I don't know.
Over reals, you can't diagonalize operators, all operators. So pure states will be a problem.
But he doesn't have operators.
Well, first I don't have operators, but certainly if you have, symmetric matrices can always be diagonalized. Hermitian matrices, real Hermitian matrices,
Real Hermitian.
or symmetric matrices can always be diagonalized. So I don't exactly see.
Cos theta, sin theta, minus sin theta, cos theta. Rotation in the plane cannot be diagonalized over reals.
Yes, that's true.
So that will create problems.
It's true, but then we have to explain why that matrix has to be. There are even matrices over the complexes that can't be
It's a real
diagonalized.
matrix, it's an over reals.
Right, I mean, this matrix, the annihilation operator. This matrix can't be diagonalized even over the complexes. So I'm not sure. But it may have something. Anyway, there's another thing that some people have pointed out is that it has to do with local tomography. I don't want to discuss it, but for those who know about quantum information, there's something called there's tomography, which is trying to deduce the quantum state from certain kinds of measurements one can do. Local tomography doesn't quite work in the real case, and it does work in the complex case, but yeah, I mean, they're all sort of interesting things, but they don't feel like the explanation. It's just like, why do we live in 4 dimensions? Well, if we lived in an odd dimension, Huygens principle wouldn't hold. But is that the reason that it's a very interesting fact, but it's not clear it's the reason why we live in even dimensions.
See, it may be that this, if you take observables and over reals. So Hermitian operator is over reals.
Yes.
It may be that the states do not admit extremals. There is this, Klein-Milman theorem.
No, I think I think it holds in the real. I think
You cannot expand it in terms of extremal states. Over
I
reals.
think that's just theory about complex sets.
There is.
I don't think it cares about the complex, if I'm not mistaken.
But this Klein-Milman, I do not think, I am not sure it goes over.
I think it does.
Okay.
But I mean, if you're interested, George Mackey wrote a whole book on foundations of quantum mechanics. He also addressed that from more the point of view that you're taking, not the one that I'll be taking. But in the end, he didn't come to any definite conclusion. He just said, there's one new observable or something. Anyway, so let me go back to getting back to the history's point of view. Let me give an example, the simplest example of a history that I can think of, which I call the two-site hopping. So it's like a particle that two-site. It's like a particle hopping on a lattice, but this is the simplest lattice that has only two locations. In time, it's discrete in space, of course, being a lattice. It's also discrete in time. So these are the two sites at any given moment, and then the particle at each tick of the clock, it either stays where it is or it hops to the other site. So here's, for example, a particular path that it might follow. So it's like a random walk. I'm not claiming it's random yet, but it's like a random walk with only two places to go to. And so, what I've drawn here, if this was the whole world, if the world was nothing but two discrete, was a sort of ladder like this in space-time, with time labels, t equals 0, t equals 1, t equals 2, and all that existed was this object hopping back and forth, or not hopping as the case may be, then a history, a complete description of reality, if we were doing classical physics, would be such a path like that, and we could notate it just by the location. So say it started here at 0, this was 0, this was 1. It may go 0, 0, 1, 0, 1, 1, 0, 1, 0, 1. So that will be a history. Okay, that's what I mean by history. And then, so there's two key notions. One is the notion of history, and the other notion is equally important, if not more so, is that of event. So what is an event? I'm using the word, Sumati mentioned this confusion with the word measure and measurement. The word event also has a confusion. Some people use it to mean a point of space-time. That's not the way in which I'm using it, although it might be that it's ultimately a special case of this kind of event. I mean it in the sense in which it's used in probability theory and the way in which it's used more like in everyday life. So it's an event that's something that can happen depending on what it does or does not happen, depending on what the actual history is. So an example of a history, of an event, is that there are more, so here's an event, just between t equals 0 and t equals 5, let's say, it spends, this hopper spends more time at the origin than it does, I'll call this the origin, than at the other location. So what is an event? Technically, it's just a set of histories, right? So I'll call this event E, give it a name. It's a set of histories for, because each history either has the property that it does spend more time at 0, or it doesn't, or it spends more time at 1. So the histories which spend more, all the histories which have this property named by the event constitute the event, as they correspond 1 to 1 with the event. So, for example, if its first 5 steps were this, 0 hops to 1, hops back to 0, sits at 0, hops to 1, see it spent 3 ticks of the clock at 0, and only 2 over at 1. So this history is in this event E. If this were the real world, then we would say that that happened. We would say, did it actually spend more time at the origin? Well, let me check. Oh, yes, it did. So that event happened. Yeah.
So an event actually has many histories.
An event is yes,
It's a collection
technically,
of
an event is a set of histories. Yes, so I should probably write that. So events. This is how the word is used in probability theory.
So event is like a microstate and your history is a microstates.
Yes, you could say it like that. Yes. Exactly, yes. And so here's another event, another history, and this history spent more time at 1, so it doesn't belong to the event E. So I could list, if I went through all possible 2 to the 5th histories, then half of them would belong to the event E in this case, and half would not.
So if you had only a finite number of steps here, then some histories could also be events. I mean, all the histories, fine-tuned, single histories are also events.
Yes, even, that's right, so there's a degenerate case where the event is a singleton history.
What is a history?
Well, I tried to, so in this case, it's just a
No,
path.
but it is, there's some space-time thing you write, you know?
Well, in this case, yeah,
No, it's like the
Is it
finite
all
number
taking
of,
place in space-time?
basically.
yes, I would say. Well, space-time or some suitable, it doesn't have to be space-time itself. So, I mean, And of course, I'm working on in quantum gravity.
Is it an
There's
ordered
causal
system?
set theory. There's no space-time as such. There's a causal set. So in that case, the history would be a causal set.
It's an ordered, partially ordered set.
In that case, yes.
That's what you mean.
No,
No,
no.
generally.
What is
That's
it?
one example.
Yeah.
It could be the electromagnetic field for all time and space, for example. That would be a history.
And what is a formal definition? Not by examples.
There is no formal definition because it varies from one field of physics to another. If you tell me what field of physics you're talking about, then I'll give you the formal definition.
By the way, when you
So what you call E is what they call sample space.
Yes, I was going to. So
No, E is not a sample.
not E, no. What the
Space
space and
and
histories
histories.
we usually following the mathematical
Probability space.
conventions we call it mega.
Probability space.
No, the samples, yeah, the sample space over which the events are
Yeah, they have
defined.
omega B P. B is what we call an event. I mean, the standard notation.
So the history space is usually called omega, and it's also called in the probability theory. It's not called history space. It's called sample space, and that's the same. That consists of the set of all histories. So an element of capital omega is one of these world lines in this case, or it's one particular electromagnetic field, or it's one particular causal set, or it's
I mean, I suppose
And
what
E is a subset
separates
omega.
now E is a subset of so each event is a subset of the space of histories, and the space of all events. I haven't given it a name. I don't know if I'll use this, but we usually call it this German this factor A. It's because it's this is a traditional name for an algebra, and the space of all events is actually a Boolean algebra in a very interesting way. I mean, a very sort of nice way that is useful for calculations. It's actually, there's a notion, this is a little side, mathematical aside, but there's a notion of addition of events, and there's a notion of multiplication of events. And under those notions, they form a Boolean algebra.
They call it the sigma algebra.
No, it's, sigma algebra, it is, sigma algebra is demanding a little bit more. So that's demanding a notion of infinite union, of countable number, countable union, and complementation. Then that's a sigma algebra. The sigma has to do with countably infinite things.
So can I
just a
think
comment to clarify, I think what Valu has. I mean, if you think of the history space as a specific class of sample spaces, where you have, I think it's important to have a time or some progression. And if you have a progression, then you call that a history space versus just a sample space like the real line, for example. Right? I mean, real line is also the sample space, and then you put
Yeah.
But how is it different from coin tossing event and asking that there are more heads, there are more tails?
it's the same.
It's not, it's
very-
exactly,
the
that's
structure
exactly
in
it.
theory is the same as that. Yeah.
But when you say progression in time, so you bring in dynamics? Or
No, just possible. So
In
there's
what
no
sense? It is
dynamics
all
is
in the
built at the
kinematic
next stage,
sense
which
you are
is this is still at the level of saying, look at all possible space-times, but without the Einstein equations, right? I mean, it's the same sort of thing.
Is it, can you think of omega as
so
some
here you are looking at the
projected
kinematic.
limit of these
Kinematic,
all
just the
possible E's?
kinematic
But there
structure
all
without
possible
concept of
dynamics.
progression
You have many
in time
E's
you
inside
use.
omega.
Progression in the sense that
Oh.
And
there
they
is
intersect
a
and so
label
forth,
that you will call
Yeah.
Label.
So can you think of omega as a projected limit of the collection of all the E's?
Projective limit of the collection of these? No,
No.
you couldn't. The way in which it arises, which will be dear to your heart, it's a kind of spectrum of this algebra. That's the nature of the connection. But you take the irreducible representations of this event algebra, and each one of them, this is not quite true in the infinite case, but the rough idea is that each irreducible representation gives you a point in the sample space or the history space. So I put here, since I probably will be using this notation in just a moment, multiplication of two events. Remember, an event is just a subset of the history space. Multiplication is just intersection. And then addition is the that's kind of a more or less common notation, although not everyone uses it. But this is very sort of less familiar. The addition of two events you might think is a union. I think people sometimes use that notation. But it's actually this disjoint union. In fact, or what's sometimes called symmetric difference. That's the thing that plays the role of addition. And if you use these definitions, then you get just an algebra in the ordinary sense, except just the scalars belong to the field Z2 instead of the complexes of the real. Yeah, I mean, this is just for those who are interested in the mathematics of this A, which we call the event algebra, because it's the algebra of all, consisting of all events. But it's kind of useful. Then the whole space itself, omega, the entire history space regarded as an event is the identity of the algebra, and the complement of an event, you might call it A prime, which is the difference between the full sample space and A. That's just 1 plus A, if you think about it. So there's just some hints on how the formalism works. But I won't be using this, none of this will I actually be using. But it becomes useful if you're really working with these ideas. So, so this is an example, the simplest example I know of in history. And an event. Let me just make one more comment on amplify what Sumati was already saying, is that these events don't happen at a particular time. To say that the particle was here at that time, that's of course an event, but it's only a very special kind of event. These events are of a space-time agent. They're, so to speak, distributed in time. There's nothing you could ask about one single time that would tell you whether it spent more time at 0 or more than 1. You have to look at the whole course of the history to answer that. Another example, I won't write anything down, but that people who think about foundations of quantum mechanics often have in mind is this arrival time. You know, if you send a wave packet at some, well, just to be moving along some one-dimensional line or something, and then you set up not a barrier, but some imaginary location, say the origin, and you ask, does the particle represented by this wave packet cross that, and if so, what's the first moment at which it reaches it? That's not something that has a definite meaning in ordinary quantum mechanics, but in different interpretations, like the Bohmian one, it has a definite one, and you can ask about arrival time. Again, arrival time is a, for example, if you ask, did it arrive between t equals 0 and t equals 5, then that's another example, typical example of an event. And one sees again that it can't be answered just by referring to any single moment of time. Okay.
So now, in this formalism, you would be able to address the question of when a particle first enters a subset.
Yes, it would have a meaning at the kinematic level. It would definitely have a meaning.
Kumar would have been happy to hear this because he keeps asking this question. And I think then the usual...
Kumar is...
N. Kumar?
Yes, I know.
Yeah.
Yeah, he's interested in this kind of question.
I
I
think
don't know that
also
specific one.
the subject of arrival time, also the POVM measures, the projection operator valued measures. So how does this way of formulation relate to POVM?
Well,
Because it has
so let me
a positive operator value. Because the questions such as arrival time or the how much time the particle spends within.
yes, I don't know how it relates to POVM, but it's easier to answer how it relates to PVM, right? Projection value measures.
Okay, so
So
that is an open question.
So a projection is just something which asks I mean, it depends. If the projection is defined at a moment of time, then, so that's not the most general kind of, then that would be a special, if it was a projection on position, some sort of position observable, then it would just define an event in this sense. It would just, like if it's a projection at a certain subinterval of the real line, say in one dimension, then it would just pick out all those histories which were within that interval at that moment of time. If it was a projection on momentum, then it's a very indirect relationship. It has no direct correspondence in this way of looking at it.
So
You'd have to actually incorporate the apparatus that measured the momentum in order to talk about it.
so that was
But
what
let me-
I was
but-
coming at, in a
but
sense,
maybe-
position space you are
Yes,
singling out.
position, in this way, position is a favored.
The favored,
distinguished
so that is what I
representation.
was-
More generally,
Yes.
when one comes to quantum gravity, I mean, I should have said probably that a lot of this was motivated by the needs of quantum gravity. When one comes to quantum gravity, or even relativistic quantum mechanics, these notions of momentum type representations don't work well. We have a space-time, but we don't have a dual object to a space-time.
So all this discussion
what I wanted to
takes
say-
position
Yeah,
preferred
I mean,
basis.
we'll have another, see what Sadiq wants to ask, but then I think maybe some of those questions that you're asking now are better asked after I've introduced
Yeah, okay,
it,
okay.
and then we can try and talk about its connection to other things.
So it's, for this particular approach, you have time steps where you are actually examining whether you are at 0 or 1. Now, that time step, is it fixed in a particular manner? Because if I scale the time step, then the answer that I get for whether a particular history belongs to a certain event will obviously change. So the question is,
Are you thinking of the continuum as underlying this?
so
No, I
or
think
is
it
there a
is-
natural scale of time?
Well,
When-
yeah, that's, in this model, there was just this discrete time. So I'm thinking of, suppose the world was such that time was genuinely discrete.
Yeah, and we would go to that lowest
Then
time
we go to
scale,
the lowest,
and,
we go to
and
the
that's
lowest.
where we would be then.
Yes, right.
There is no quantum mechanical system corresponding to this system. This is a toy model from which you
Sure. Yeah, it's just that, I mean, if the time is not discretized, then you can always scale and then the
No,
events.
no, so if
take
your
part.
time is
It's
not
a-
discretized, the way of describing this will be far more complex, but there exists a way, and I think that in all these examples, one is trying to simplify
Sure.
to the extent possible so that you're not dealing with a lot of. But you can do the whole thing in the continuum as well, but then the discussion is more sophisticated in some way.
Yeah, at the mathematical level, you're asking about what I described here was kind of random walk, and you would be asking how is that related to Brownian motion, or the Wiener process as it's called, which is a continuum, and that's a complicated story if you try and do it really fully rigorously. But roughly speaking, the one is the limit of the other, just in the way you said. But here I'm just describing a world in which the limit is meaningless, and time really is discrete, and then we go to the minimum. The history is the most complete description you can give of the reality.
No,
And so that would be going to this minimum time step.
the point is if we go to the next level of discretization, which is we only consider time steps which are two.
Yeah.
You know, and then, I mean, you could always scale up. and
That's
also
So
right.
there
press
has to be a
it down.
coarse graining of the
So
system.
what
Coarse
that-
graining,
what-
etc.
Yeah, what
And-
that coarse graining actually does is it replaces this algebra by some, say, the event, it means you consider only certain events. Like you consider only the average location over pairs of times or something
Yes.
like that. Or some blocked set of, and so that what that means technically is that you consider a subalgebra of the algebra events. You consider only certain events, certain questions. You only allow yourself to ask certain questions about the history. In fact, I meant to say at some point, so let me say it now, that an event can be thought of as a question that you ask about the history. And then the set of histories that answers the question yes is the set that we identify with that event. So like before I ask, does it spend more time at the origin or more time at one? That's a question you can ask. And those histories for which the answer is yes constitute the event in the technical sense. So I think so this was all kinematics, all this which I just partly erased. Kinematics here sort of what are we talking about, and then dynamics is what is it, how does it act? So first we have to decide what we're talking about, and what we're talking about is, in this case, histories and sets of histories. So the history space omega